Hi guys, so this is the Unit 3 study guide key worked out video. Now I'm going to start with piecewise functions. Let's go ahead and graph this function first. So we see that the function has three different parts, or it's made up of three different equations. I see two linear functions and, well, all linear. One has a horizontal, a slope of 0. So the easiest way to do this is to take into account the parameters that you have to use, but also just to actually graph the function all together, and then you can kind of erase or know where to actually plot the points. So let's look at the first one. Okay, it starts at -1 on the y-axis right here. Okay, and I'm going to go up 1 and to the right 2. But notice that the parameters of that, the inputs, have to be less than -2. So I'm going to go down 1 and to the left 2 right here. Down 1 and to the left 2. And so there is my hole. I can erase these. There's my hole. And down 1 and to the left 2. Down 1 and to the left 2. I'm going to try to fill this in. So it gives me a nice little graph. And then the next one starts at 2. And it goes down 3. 1, 2, 3. And to the right 1. But I also have to see what happens at -2. So up 1, 1, 2, 3. Here, 1, 2, 3. One, 2, 3. And here we have a circle, open circle right here at 1. There's the rest of my line. -2 is a closed circle here. And at starting from 1, it is a closed circle and goes all the way to the right. Okay, good job guys. For number 2, we have an interesting looking function right here. That's an exponential. I'm going to go ahead and I'm going to figure out what happens at this hole. Okay, I know that this is not equal to, but I still have to figure out how I'm going to graph that. So let's go ahead and put a -4. And that negative exponent is going to take that entire thing, the base, -2, and the 4. And what we assume is we have to do exponents. So what we assume is that we have to do the exponent first before we actually tag that negative on. There's a difference between this, which does not equal this. This tells us that we have to first make that a positive exponent by moving the entire base and whatever it multiplies outside down to denominator, and then that becomes -16 because you're raising 2 to the 4th power first. Now this, we are taking that entire with the parentheses, putting in the denominator, and then if we raise it to the 4th power, it becomes a +16. So if it doesn't have any parentheses, then we assume that we do the exponent first. So that's over -16. Okay, which comes to be around -0.0625. Let's go ahead. We need to get further We need to get smaller. So we have a -5, which is going to be a -2 raised to the 5th power, -2 to the 5th power. 2 to the 5th power is a 32, is it? 2 to the 5th power. Yep. And so that's -32, which comes up to be about -0.03125. When I graph that, it looks like it's getting closer and closer to 0. Okay. And so you have a -4, open circle, and then -5, open circle, and just, close circle. Something that looks like that. Okay, and then we have to do the absolute value. The absolute value is between -4. I'm going to take a -4 in here. Absolute value of -4 is 4. I'm using this function now. -4, and then 4, -4. So -4, -4, that's a closed circle because it equals. And then let's try 0. 0 is 0. And that equals. There's that. And then we have a quadratic here. And I need to figure out what happens at 0. I know that that is going to be a whole. Figure out what happens at 0. It's going to be a 4, 0, and a +4, but okay. And then it's like a quadratic. And I think that's the vertex. So let's just put a point there. I don't know, I can put a +2. +2. It's going to be at 2, 0. It's going to look something like that. Okay. So quadratic, making sure that I have my open circles where it needs to be. And good job, guys. Okay. Number 3. Let's go ahead and graph this. Let's see, we see an absolute value, a 4th root. It's like a polynomial function. But it only equals this here, at x equals 1. So I'm going to make a table. And you don't have to make a table. And you can just draw it on here. But for me, I like making tables. I need to figure out for the first function. I know that's a whole, but I need to figure out what happens there at 1. So I put a 1 in. 1 minus 3. It's going to be a -2, so a +2. 1, +2. There's my whole. Let's go ahead and figure it. I know the vertex. It's going to move right 3, so I know that its vertex is going to be this right 3 somewhere here. But it doesn't include that point because it has to be less than. So I know that it's just going to be a linear function from there. Oh, wait a second. It starts at 1. What am I doing? So 1, 1, 2. It starts right there. So I could put a 0 in, and that's going to be a 3. And then my slope is just going to become 1. 1 over 1, 1 over 1. And I could test it out, but that's going to be just a 4. So I know that for x, because I know it's going to go positive slope from there on that absolute value function. Okay, now let's go ahead and see what happens at 1 for this particular function right here. Because that's only true, you only use that for the input of 1. Okay, so 1 and 1, that's 0, so it's going to be 0. So 1, 0, I'm going to put a closed circle there. And then let's see what happens at 1 for this particular function. I know it's a hole there, but I just want to see. Square root of 4 is going to be 2. 1, 2. There's kind of connects at that absolute value function. Let's go and put in another point, like 2. 2 times 4 is going to give me 8. I could put a 4 in. It's going to give me a 16. That's 4 over 4. 4, 4. There we go. It's a square root function. It's going to look something like this. Oh no, I drew it wrong. Sorry. It should connect right here. Okay. Good job. Okay. Write the equation of the piecewise function. What I see is that the slope of this line is different than the slope of this line. Is it? Yeah. I could see that I could use this point and this point right here. Looks like, but I could see those points are where it exactly intersects at an integer is off. So I can tell that the slope of the line is going to be different. So f of x equals, let's go ahead and find this positive slope first. I have 2 points. I have -2, 3, and -4, -1. Okay, slope is going to be 1, 2, 3, 4, down, 1, 2, 3, 4 down, and 2 to the right. I guess that's a point there too. So the slope is going to be a +2. If I keep on taking that slope, +2 to the right, +2 to the right, it's going to be 2x plus 7. Or you could find the slope using these 2 points if you wanted to. But if you know slope, you could keep on counting up. And if it's on a graph, then you can find the y-intercept. Okay, I'm going to erase all of this, especially this part right here. Those were solid. So I could put, definitely, it starts at -6. I have to put the equal sign there. I can put either the equal sign at -2 on this function or the next one. I'm just going to choose this one. Okay, let's go ahead and find this line right here. I don't see any other integers. I go down 1, 2, 3, 4, 5, down 5, and right 2. So that is down 5 and right 2, down 5 and right 2, and my y-intercept is going to be -2. It starts at -2 right here, but I can't put the equal here because if these two equals overlap, then it's going to be wrong. So it's not going to be a function. Okay, and then x, and it goes all the way to +2. And then I have the horizontal line with this line here, and that is going to be an output of 7. It starts at 2. Here's my equal. Yeah, x is greater than or equal to 2. Okay? Good job, guys. Next one. Number 5, write the equation of the piecewise function. Okay, let's go ahead and break that up. Looks like I have 1, 2. That right there looks like an absolute value function because I could see that the slopes are the same. I could write this as an absolute value function if I wanted to, or I could break it down into 2 linear functions. It doesn't matter. Okay. So let's go ahead and write f of x equals, let's see, what's a good point? That point right there. So that's going to be -4, -3, -6, -2. So I have to go down 1 and to the right 2, down 1 and to the right 2, 2x. And to figure out the y-intercept, I can take those 2 points. And so I'm going to use y equals -1/2 x plus b. Find my b. -2 equals -1/2, -6 plus b. So 2 equals +3 plus b. So b is going to be -5. Move that down. -5. And the inputs that I can put in is less than or equal to -4. Okay. Let's go ahead and find this line right here. I'm going to use this point, -4, -3. And I can actually use that point right there. Looks like a good intersection. That looks like a -3, -1. Okay. The slope is going to be up 2 and to the right 1, 2x. If I take that point and I use the slope up 1 and to the right, that's going to be a 5. There's my y-intercept. Now it's going to be in between -4x and -1. Okay. Now I'm going to go ahead and write that as an absolute value function. Absolute value function with a slope of 1. Slope of 1. It keeps on just increasing as 1. So that is going to be an absolute value of x minus 2. X minus 2. And that is between -1 and, well, infinity. But we don't write infinity like that. There's still kids that are writing infinities like that. We don't put infinities in inequalities, guys. Okay, now if I split that up into 2, the slope is going to be 1 for each one. Okay, or let's go ahead and show you the alternative one. Okay, f of x, the 2 first equations are going to be the same. These 2 are going to be the same. If I break that up, the y-intercept of this line right here, slope is still 1, is going to be a +2. And that's a negative line, so -x, +2. And that's going to go from -1 to 2. And then of this right here, that's a positive slope. And if I keep on going down, it's going to be here, down here, down here. The y-intercept is -2. That's a positive slope. X minus 2. And x has to be greater than 2. Whoops. Now if I took this absolute value and I rewrote it without the absolute value, it would be x minus 2, and I would have to take the negative of both, and that's basically the two equations that you get from it. Because when I remove the absolute value, I could write it as whatever's inside as 1 with a positive, multiplying both x and minus 2, -2, or I have to multiply x minus 2 by -1, which gives me a -x plus 2. So it's the same. Okay, next one. Let's go ahead and write this one. So I have 1. It looks like a linear function that looks like a quadratic. Let's see. So f of x equals, and the linear function output is 0, and it's when x is less than -4. And then let's see, the slope of that is 1, so that is going to be just an x, and that is when -4 between x and 0. Oh, what you guys didn't see is the line, the horizontal line. Oh, that's right. Oh, it overlapped. It didn't print very well. I'm sorry. You guys probably didn't see this red line here. Okay, that's probably why. I think Megan asked about it in class, and she just saw the little hole, and I said it's useless to put that, but anyways, yeah. I think most people just saw a hole there. It was actually a red line. You didn't see it. Okay, the parabola. It looks like the vertex of the parabola is 0, +4. So I can go ahead and write the vertex as, so it's going to be y equals a, x plus 0, which just could be that, and then +4. And then I can use this point right here, which is 2, 0, 0 to find a. Subtract 4, 4a squared. It's going to be a -1 equals a. Oops. It's going to be a -x squared plus 4. And it's x when x is greater than 0. Okay? And that's the final answer. Good job, guys. Okay, let's do composition of functions, which was the second lesson that we did. Okay, and this one's pretty straightforward. I think, I don't think we did this, but if you understand what the composition of functions is, then I don't think you should have a problem. This basically says that the input function is g. Okay, here's function g, and here's function f. And what you're inputting into g, is a 2. So when x equals 2. So in the g function, when x equals 2, here's 2 right here. What is the output? 2, 3, 4, 5. It is 5. Now I'm going to take that and I'm going to put it into the next function, which is f. Okay. Now if I put it into f, 5, here's 2, 3, 4, 5. Right here, it's going to give me a 4 as an output. So therefore, f of g of 2 equals 4. Okay. Here the input function is f. So I'm going to put that input into the input function. Function 4, it looks like it's right here. That's a 2. It gives me an output of 2. Implies. And then that implies that I'm going to put the 2, let's put it in different colors. I'm going to put it into G. And when I put the input of G of 2 into G, that's going to give me a 5. So therefore, G of f of 4 equals 5. This implies, first I'm going to put the negative 2 into G. G, there's negative 1, negative 2. That's going to give me an output of a 1. And then I'm going to put that back into G. That input of 1 right here. And that's going to give me a 4. So therefore, G of negative 2 equals 4. Now I'm going to first use function f to put in that input of 0. Put in the 0, it's going to give me an output of 0. Now it tells us to take that output of 0 and put it as an input of G. 0, right there, it's going to give me an output of 3. Therefore, G of f of 0 equals 3. First, my input function is going to be G. So I'm going to put 0 in. Put a 0 in into the input function. That's going to give me 1, 2, 3. I'm going to take that output. And make it an input into my f function, which is going to give me a 0. Right? So therefore, f of g of 0 equals 0. I think that's right. 3 for G, and then F, put in it 3, and it's going to give me a 0. Okay. Let's see. F of G of X. It's asking us to find the inverse of that function. Well, the identity function. Well, is it? Any number that I could put in for true, and then input. It's asking us to find the inverse. I'm going to skip this one. I think this is a typo. I think there should have been a number in there. Okay. We could make it F0. But then that'd still be 0. I could make it a 2, 2. Let's try and make it a 2. Let's try and make a 2 in there. Okay. which means that at 2, you get an output of -2. Oh, wait a second. If I put a -2, it's going to give me an output of a -2 at f of 2. But then when I put f of -2 back in, it's going to give me an empty set. It's going to give me an empty set. And there's no output that comes out of -2, f of -2. Okay? Just made one up. Number 7. It says find f of g, g of f, f of f, g of g, and state their domains. Okay. Let's go ahead and find f of g. F of g. I'm going to open up that input function right there. So you minus 4. That you can't go any further. You can't break that out. You can create 2, and you can say x plus 4, and you can say negative x minus 4 if you wanted to, and create 2 different functions, but and make it a piecewise function. But I'm just going to keep it as is. The domain. Let's go ahead and state the domain is all real numbers for this, and for g, it's all real numbers. So we look at the domains of both of the composition, well, the input function, which was g, and then we actually look at the function itself, which just becomes an absolute value function. So that's the domain. There are no restrictions. So the domain of f of g is x such that x is an element of all real numbers. And then let's do g of f. Let's open up x, put in the f. You get something like that. That is going to give you implies. Oh, I wanted to put all the correct answers here. Going to be x minus 4, so it's going to be the absolute value of x. And once again, there is no restriction on that. Domain. And then f of f. Open that up, put x minus 4 minus 4, which ends up becoming x minus 8. The domain of that function, linear and linear, so therefore all real numbers. G of g, it's an absolute value inside of an absolute value, which is very interesting. But we have to keep it the way it is. Domain of g, x, all real numbers. And once again, you can write it into 4 different piecewise functions, or piecewise function that has 4 functions in it. But I'm not going to do that. Okay. Here we go with this one. Number 8. We do f of g. Open up f. And where x was, I'm going to put that. But then we can't have a radical in the denominator. So I'm going to take a conjugate, multiply by its conjugate. So I get the square root of x plus 4 plus 2 over x plus 4. When you multiply square root of x plus 4 is going to be x plus 4. And then the middle term cancels out, so you get a minus 4, which is x plus 4 plus 2 over x. Okay, let's take a look at, let's go ahead and identify the domains. Domains of this x cannot be 2. Okay, we can't have the denominator be 2. For g, it has to be x is greater than or equal to 4. Okay, take that radicand, we set it greater than or equal to 0, and then, or is negative 4, I'm sorry. Negative 4. And so what was the input function? What it already got restricted with what we could put in the input. The input function was d of g, which is x is greater than or equal to negative 4. And then if you look at the composition function right here, we look at denominator, we say that x cannot be 0. So therefore it's going to be, it can be greater than or equal to negative 4, but it can't be 0. So the domain of f of g is going to be x such that x, then negative 4, x, 0, and the union greater than 0. Okay. Greater than 0, or it has to be between negative 4. It could equal negative 4 or 0. If I put it on the number line, it's going to look like it can't be 0 and negative 4. Here, here, and all of this here. So you have to get this little, all of this here. So you have to get this little area, which is the negative 4 to 0, doesn't equal 0, and here. You'll need 2 inequalities. Okay. Next. Let's see, we need to do g of f. Whoops. G of f of x equals go ahead and then somebody's going to realize that I need to label these, and somebody's not going to label them. Okay, g of f is going to be, the input function is f. I'm going to open this up, and I'm going to put 1 over x minus 2 plus 4. Kind of clean that up. So that's going to be 1 over x minus 2 plus 4 times x minus 2. I'm going to go ahead and combine that. X minus 2. You're in my way. Okay, and that's going to be 1 plus 4x minus 8, x minus 2 equals square root of 4x minus 7 over x minus 2. Multiply top and bottom by x minus 2 because we can't have a radical in the denominator. Okay, I just need a little bit more space. So that is going to be the square root of 4x minus 7, x minus 2 over x minus 2. It can come out of the radical. Let's look at what domains. Domain of the input function of f was x cannot be 2. The composite function also here. So x cannot be 2 either. So it just has a restriction of 2. So we have, let's go ahead and write the full thing of x equals square root of 4x minus 7, x minus 2 over x minus 2. And the domain of g of f is going to be x such that x is an element of all real numbers, but x cannot be 2. Here we go. Okay. Okay, on to f of x. So let's go ahead and open up our input function. And where x is, put f back in. This is going to give us 1 over 1x minus 2 minus 2 x minus 2 over x minus 2. Let's go ahead and make it go sideways. And then 1 over 1 minus 2 x minus 2 over x minus 2. And basically what we just have to do is multiply by 1 and take the reciprocal of the denominator. So when we take the reciprocal of the denominator and multiply it by 1, it just becomes the reciprocal of the denominator. So we have x minus 2 that used to be the denominator in the denominator now become the numerator of the whole thing. And then we just have 1 minus 2x plus 4. So x minus 2, negative 2x plus 5. Okay, and then let's see. The function itself of f, the input function, had x could not be 2. The composite function has negative 2x plus 5, cannot be 0. So that's x cannot be negative 5 and 5 halves. Okay, so it excludes those two. So f of x was x minus 2, negative 2x plus 5. And the domain of this function is x such that x is element of all real numbers, x cannot be 2, and x cannot be 5 over 2. Okay. The last one, g of g. G of g. So g, open that up, and then now we have x plus 4 plus 4. Okay. You can write it this way, or you could say that it is x plus 4 raised to the 1/2 power, and then you add 4 to it, and then you raise the entire thing to 1/2. I mean, it's either way, it's still the same thing. It doesn't really matter. Okay, and the domain, the restriction of the domain was the input function was that x has to be greater than or equal to negative 4. And let's look at the entire function. If there was a restriction on that, if that equaled 0, x plus 4, then that entire thing, I think we pretty much took care of all the negatives, that it's not going to, yeah. I mean, we could take the radicand, square root of x plus 4 is it equal to 0? Square root of x plus 4 is greater than or equal to negative 4. Equal to negative 4. And then in order to do that, you have to square both sides. And the square root of x plus 4 is always going to be greater than or equal to negative 4. Well, if we put in, yeah, because if we already set the restriction of the input domain as greater than or equal to negative 4, and the only number that, the smallest number I could already put in, because this, remember, this right here came from the input function. I'm trying to find out the composite function's domain, and this is where I am. But if I already set this restriction, the lowest number that I could put in is a negative 4, And if I put a -4 in here, -4 plus 4, you get a 0 is greater than or equal to -4. So it's going to work every single time. So that's very restrictive already. And it works for the input function. So I'm going to just put that. And you can put a -3 in there. It already works. I mean, yeah, it already works. So G, let me go ahead and write it off to the side. So G of x equals the square root of x plus 4 plus 4. And the domain of this function is x such that x is greater than or equal to -4. Okay, good job. Okay, number 9, just make sure. Let me just remember, f of g. I'm going to do f of g first. Take -9, x minus 5 in it. That's going to be 1 over x minus 5 minus 9, x minus 5 over x minus 5, which gives me 1 over 1 minus x 9x plus 45, x minus 5, which is just going to be x minus 5, negative 9x plus 46. It's 46. Yep. Okay. So f of g of x equals x minus 5 over negative x plus 46. I could define domain of f, x cannot be 9. Domain of g, x cannot be 5. What was my input function? The input function was g, so that restricted the 5 from going in. And then I could take the composite function, set it not equal to 0. Negative 9x cannot be negative 46, so x also cannot be 46 over 9. Whoops. So the domain is going to be x such that x is an element of all real numbers. My input function was g, so it cannot be 5, and x cannot be 46 over 9. There it is. Okay, the next one is going to be g of f I'm going to take g, open up where my x is, input f, one over x minus 9 minus 5 times x minus 9 over x minus 9 equals 1 over 1 minus 5x plus 45 over x minus 9 . So that's going to be x minus 9 over negative 5x plus 46. Okay, so the domain is going to restrict the input function's restriction, which is 9. And also the denominator, negative 5x plus 46, cannot be 0. So x cannot be 46 over 5. So g of f of x equals x minus 9 over negative 5x plus 46. Domain is x such that X is an element of all real numbers. X cannot be the input function restriction, and X cannot be the composition function, the composite function restriction. There you go. Okay. Next, we are going to do f of x open up x minus 9, 1 over 1 minus 9, x minus 9, x minus 9. That's going to equal that. 1 minus 9x plus 81. X minus 9 over negative 9x plus 82. Let's see, so f of x equals x minus 9 over negative 9x plus 82. The domain is going to restrict the input function's restriction, which was f. So f was x could not be 9. X such that x is an element of all real numbers. X can't be 9. X cannot be this denominator either. See, 82 is it divisible by? Nope, it's not divisible by 3 either. 10, nope. So it's going to be an 8 and sorry. X cannot be 82 over 9. The last one. Let's make some room for it. I'm going to do g of g now. G of x. G of g is 1 over x minus. I'm going to open up 5 minus 5 equals 1 over 1 minus 5, x minus 5, x minus 5. That's going to equal x minus 5 over 1 minus 5x plus 25. So g of x equals x minus 5 over negative 5x plus 26. The domain, it's going to restrict the g input, which is x cannot be 5, and also x cannot be 26 over 5. Okay, next one. Let's go ahead and write down what I have to do. I have to do f of g, g of f, f of f, and g of g. The domain of this function is all real numbers. The domain of g is going to be x is greater than or equal to negative 9. Okay, let's do f of g of x. Find out where g is. X plus 9 squared minus 3. So we have an x plus 9 minus 3, x plus 6. We have a linear function, but we know that that linear function got created from composition of two functions. So what was the input function and what was its restriction? That x had to be greater than or equal to negative 9. So x such that x has to be greater than or equal to negative 9. Here is the correct answer. And then g of f of x. Let's open up x plus 9 I'm going to put x squared minus 3 plus 9. And that's going to give me x squared plus 6. That's as far as we can take that. As far as I can take that. And so therefore, the input function was all real numbers. Function f, domain was all real numbers. I could take x squared plus 6, make it greater than or equal to 0. X squared is to be greater than, x squared greater than or equal to negative 6. When you square an x, any kind of input, it's going to make it positive. It could never be a negative, so this is always true. So the domain of this, you can put anything. X is all real numbers. Because this is always true. Okay, let's do f of f first. Yes. F of f of x. Let's go ahead and open up that square. Put another square in it. Minus 3. I mean, you can expand that out if you want. Yeah, I am going to do it. X to the 4th minus 6, x to the 2nd plus 9. And then minus 3. X to the 4th minus 6x squared plus 6. That's f of x. The input function was all real numbers. The composite function is all real numbers. You can put in anything for x. So the domain of this is x such that x is an element of all real numbers. And then let's do g of x. Put that. And once again, we're going to have a radical inside of a radical. The restriction was has to be greater than or equal to negative 9. X has to be greater than or equal to negative 9. And I mean, if I take this radical, the composition of function and make it greater than or equal to 0, x plus 9 is greater than or negative 9. And I already restricted x to be greater than or equal to negative 9. So this is always going to be true. With the case if I make x is greater than or equal to negative 9. So that I could set as my restrictive domain. There you go. Okay. Good job. Okay. Next one, number 11. Okay, let's do f of g. F of g of x. F of g function, take f, open it up. X plus 2. And then that's just 2 divided by x plus 2, which equals 2 times x plus 2 over x. So that is just f of g of x is going to be 2 times x plus 2 over x. Okay, the restriction of f was that it can be 0. G could not be x, the domain of g, x could not be negative 2. Okay. So the input function restricted x cannot be negative 2, but the composition of function also restricts 0. Okay. Next g of f the input function is g, so I have to put 2x here and 2 over x here. So I get 2 over x over 2 plus 2x over x. Remember, the denominator and the numerators is the same. I mean, the denominators of the two compound fractions is the same, so I could just put 2 over 2 plus 2x. I could simplify g of f of x, every single coefficient. I could simplify it 2, or I could rewrite this as 1 plus x. And so I get 1 over 1 plus x. Okay. And then let's see, my restriction for the input function of f was that x could not be 0. Here, x cannot be -1. Okay? Good job. Okay, next one. Let's do f of x, f of x. I'm going to take that, put that in like this. So I get 2 divided by 2 over x, which is 2 times x over 2. So that just cancels out the 2's. So I get an x. F of x equals x. The input function was f, and so that could not be. The domain restricted to 0. Okay, and so x is all real numbers. X can't be 0. The composite function is a linear function, y equals x, which is all real numbers, so it doesn't have any restrictions. There you go. Okay, the last one. So let's do g of x, which is going to be the fun one. Okay, x over x plus 2, where that numerator x is. X plus 2 plus 2. X plus 2 over x plus 2 times x plus 2 over x plus 2. The numerator and denominators are the same, so I can actually cancel them out. X over, I get x plus 2x plus 4 equals x plus 3x plus 4. So g of x equals x over 3x plus 4. My input function restriction was x cannot be -2. And my composite function restriction is that x cannot be -4/3. Okay. Good job. Okay, the last one of these. Right here, let's do f of g of x. Here, the domain of f is going to be x is greater than or equal to 0. The domain of g is going to be all real numbers, except x cannot be 4. Okay, let's go ahead and open up f, square root 2 over x minus 4. We can't have square root in the denominator. I'm going to go ahead and do that. So it becomes the square root of 2 times x minus 4. X minus 4 comes out. Okay. The composite input function was g. The restriction for g was x cannot be 4. So f of g of x is the square root of 2 times x minus 4 over x minus 4. The domain is going to be x such that x is an element of all real numbers, but we have to restrict it for 4. And the composition of the composite function also has an x minus 4 in the denominator, so which tells us that it just can't be 4. Okay? And then we have a g of f of x. I'm going to open up this square root x minus 4. We can't have a radical in the denominator. I'm going to multiply top and bottom by the conjugate. So I end up with a 2 times square root of x plus 4 over square root of x times the square root of x is x minus 4 square root of x plus 4 square root of x. Cancel out that middle term, minus 16. So g of f of x equals 2 square root of x plus 4 x minus 16. Let's see. So the domain of the function x, the input function was f, so x is greater than or equal to 0, all real numbers. It can't be equal to 16. Hold on. This implies that x cannot equal 16. So yes, it could be all the numbers that are greater than or equal to 0. Go ahead. Okay, 0 like this. But then 16, it can't be 16, so you have to take this into two inequalities. So x could be between 0 and equal to 0, 16, and x has to be 16. There you go. There is the domain. Like that. Okay. Let's do f of x. Yep, f of x, g of x. Okay, g of f. Okay, that's going to be just a square root and a square root of x. I could rewrite this as x to the 1/2, which is x to the 1/4. Okay. Or the 4th root of x. Okay, this you can actually simplify. So f of x equals the 4th root of x, or x to the 1/4. And x has to be still greater than or equal to 0. It's true. It still holds true. Because it's just an even root. So that domain of the input function is going to still hold true. And that's the only one that holds true. Okay. Let's see. So we have a g of x. What was g? Okay, so 2 over x minus 4 minus 4. 2 over 2 minus 4 x minus 4 over x minus 4. So that is 2 over 2 minus 4x plus 16 over x minus 4. That equals 2 over negative 4x plus 18 over x minus 4. Go ahead and take the reciprocal. 2 times x minus 4 plus 18. So that becomes 2x minus 4. I'm going to take a negative 4 out from there. Negative 4. Can I take a negative? No. Negative 2 out. Let's go ahead and take a negative 2 out. Negative 2 out. That becomes 2x minus 9. Okay. And then I can reduce this, and it becomes g of x equals x minus 4. We still have the negative out here. And 2x minus 9. I'm going to distribute that through. It doesn't matter. It's not going to change my domain. Okay. I could put it on the top with the parentheses. It doesn't matter. Okay. Let's go ahead and simplify. Implies that g of x equals x minus 4 over negative 2x plus 9. Let's look at the domain of this function. What was the input function that it could not be? X could not be 4. But now x can also not be 9 over 2. Okay? There we go. Good job, guys. Justify using composite of function that these pairs of functions are inverses of each other. In order to prove that they are composition of function, inverses of each other using composition of function, you have to prove that f of g equals x and g of f also equals x. You have to prove both. Okay? You have to. That's just an algebraic proof. Okay. And the way you solve an algebraic proof is you make one side stay as is, and you just move the left hand or the right hand side, and you have to have the left hand side equal the right hand side. Okay, I'm just trying to prepare you for SL math. Okay, so let's go ahead and prove f of g of x equals x. I'm going to take my input function for x plus 4. Does it equal x? Negative 4 plus x plus 4 equals x. X equals x. Check. Okay, and then let's go ahead and prove g of f equals x. 1/4 g negative 4x plus 4 equals x. 1 plus x minus 1 equals x. X equals x. So therefore, f and g are inverses. Okay. Let's go ahead and prove f of g of x equals x. Negative 2 over x minus 1 minus 5 over negative 2 over x minus 1 minus 3. Does it equal x? Negative 2 minus 5 times x minus 1 over x minus 1. Negative 2 minus 3 x minus 1 over x minus 1. Equal x. Proof continues here. So I have a negative 2 minus 5x plus 5 over x minus 1 over negative 2 minus 3x plus 3 over x minus 1. The denominators of the compound fraction are equal, so I could just cancel them out. So I end up with a negative 5x plus 3 over negative 3x plus 1 equal x equal x. No, they don't equal x. Okay. I mean, pretty much I could just stop there and say that they're not inverses because one of them is not equal to x. So since f of g of x does not equal x, therefore f and g are not inverses. Okay. F of g of x should equal x if they are inverses. Open up the x. Gosh, that's going to be a big drop. I'm going to put the entire cube root over 2 plus 3 cubed over 2 should equal x. The 2 gets multiplied out, 2 over 2. So we end up with a cube root of 2x minus 3 plus 3 cubed over 3. Okay, and then, well, that looks just really ugly. That gets canceled out. So we have the cube root 2x minus 3 plus 3 over 2 equals x. And then that just becomes a cube root 2x raised to the third power over 2. Okay, and that just becomes a 2x over 2 equals x. X equals x. Prove that one. Let's do g of f of x equals x. Cube root 2. I'm going to put that entire thing in there. 2x plus 3. I think this was a homework problem. Over 2 minus 3 over 2. And I just liked it so much that I put it back in here. Okay, and that gets canceled out. So you end up with, wait a second. That's not right. It's not supposed to go all the way. The minus 3 is outside. Okay, and then it's a cube root of 2x plus 3 raised to the third power minus 3 over 2. We have raised to the third power and a cube root, so whatever's inside that radicand just comes out, except for the raised to the third power. 2. All of these we have to check to see if it equals x. So 2x over 2, x equals x. So therefore, f and g are inverses. Okay. Let's do number 4. We need g or f of g. F of g of x should equal x. So open up, oh no, I'm sorry. Let's do g of h. Negative 3 fourths. Open that up. Drop in. Be careful. Be very careful where you put that negative sign. Minus 20 over 3. I'm going to tag it along on the negative sign right here. I'm going to put it down on the negative 3. Because if I put it in the numerator, I have to distribute. I don't feel like distributing. And the denominator only has one term. I could completely cancel this out. So I end up with a 4x minus 20 divided by 4. So that's 4x over 4 minus 20 over 4. X, so that's x minus 5. X minus 5. I don't think it will work, buddy. Oh, wait a second. Oh, I forgot the plus. That's right. I forgot the rest of the function right here. Plus 5. Plus 5. Plus 5. Plus 5. Plus 5. So x equals x. Let's go ahead and try h of g of x negative. I'm just going to go ahead and put the negative on the 3 in the denominator. 4, open that up, negative 3/4 x plus 5 minus 20 over negative 3. Whoops. And that should equal x. Okay. Distribute the 4, so that's a negative 3x plus 20 minus 20 on negative 3 equals x. Negative 3x divided by 3 equals x. Negative 3. Okay. So x equals x. So therefore, is it g and h functions g and h are inverses. Okay. The next set of problems asked you to just find the inverse. And I have no idea why I picked all. Why did I pick all rational functions? Okay. Probably because I want you to practice rational functions, which is always the case every single year because we have the hardest time. So you have y equals 1 over x plus 2. You switch the x's and y's. And here, to try to get that y in the denominator out, I'm going to multiply both sides by the denominator. So let's go ahead and distribute that x. So we get an xy plus 2x equals 1. I'm going to move the x to the other side. So that's plus 1. And then divide both sides by x. So you get y equals negative 2x plus 1 over x. And it's pointless splitting it apart because you're really not going to simplify. Well, you're going to simplify the x, but this is basically what you get. Okay, and then we always have to state that x cannot be 0. Negative 1, x equals 1 minus 2x over x. And if you don't state the restriction on the denominator, I'll be fine because we really haven't gone over like a real unit over rational functions. Okay, so y equals x minus 2 over x plus 2. Switch the x's and y's. I'm going to multiply by the denominator once again. Distribute xy plus 2x equals y minus 2. Right? Y minus 2. That spreads the y's out. It spreads the y's out, so I'm going to gather the y's on one side and move everything to the other side. I'm going to factor out a y. and then divide by my factor. So y equals negative 2x minus 2, x minus 1. Okay? So f of negative 1, x equals negative 2x minus 2, x minus 1. Okay? Y equals x plus 4, switch the x's and y's. Multiply both sides by the denominator. Distribute the x through on the left-hand side. Gather the y's on one side and move everything else to the other side. Factor out the y. Divide by the binomial after you factor out the y. So f of negative 1 of x equals negative 4x, x minus 1. Oops, kind of cut off. Okay. Next, y equals 3x minus x minus 2. Switch the x's and y's. Multiply both sides by the denominator. Distribute the x. You're left with a 3y. Gather the y's on one side. Move everything to the other side. Factor out the y. Divide to isolate the y by the binomial. Oops. How did this happen? F of negative 1 of x equals 2x over x minus 3. There you go. Okay, next one. I think I'm going to need more space. Y equals 2x plus 3 over 1 minus 5x. Switch the x's and y's. Multiply by the denominator. Distribute the x. Gather the y's on one side, everything else goes to the other side. Oops. Factor out the y. Divide both sides by the binomial that you factored out. So f of negative 1 of x equals 3 minus x over negative 5x minus 2. Okay. Plus 2, x minus 3. You can have different variation. You can take an negative out on both the denominator and the numerator. It's the same answer. Y equals 3 minus 4x. Switch the x's and y's. Multiply by the denominator. Distribute the x. Okay, you're left with the numerator. Gather the y's on one side and everything else to the other side. Factor out a y. Divide both sides. So f of -1 of x equals x plus 3, 8x plus 4. Whoops. Okay. Okay. It says find the inverse of the function. Remember, you must choose one function from plus or minus to match the domain of the function, or must restrict the domain of the inverse function. Okay, so this is a quadratic, but it's given the restriction already. Okay, so if this is the case, we can actually find the inverse function of this. Remember, this, if without that restriction, would be a many to one function. So we would not, you couldn't even find the function, the inverse function. But since we made it and restricted it based on the axis of symmetry on one side, now we can. Okay, so y equals 4 minus x squared. Switch the x's and y's. Move the 4 to the other side. Divide everything by -1. So you end up with a negative x plus 4 equals y squared. I'm going to take the square root. I get plus or minus x plus 4 equals y. Okay, so we have to figure out which one we choose, the plus or minus. Whoops. Well, we can do that by looking at the domain and range of the original function. The domain of the original function was x such that x is greater than or equal to 0. Okay, and then the range of the function was, it's reflected over the x-axis, and so we could do the same thing as we did for the radical. We could take y and set it greater than or equal to. We could multiply by x squared. That's what is happening right there. But when we multiply both sides by -1, it also flips the sign. Okay, and then we add 4. So we add 4. So y is less than or equal to 4. We can do the same thing. Okay, so the domain of the function has to be greater than or equal to 0. So we know that that's going to have to be the plus 1. Because if we have a plus square root of x plus 4, okay, is greater than or equal to 0, that's just, yeah, you don't have to change anything. But if we had a minus square root of x plus 4, and it was greater than or equal to 0, to get that minus, we multiply by a -1. So that has to be multiplied by a -1, and that has to be multiplied by a -1. So the negative portion is going to give me less than or equal to 0. And I need the range of this function, the inverse function, in order to be greater than or equal to 0. So I'm going to choose the positive. F of -1 of x is going to be the positive square root of x plus 4. And I can state the domain of the function is x is greater than or equal to 4. And the range of the function is now y is greater than or equal to 0. Okay? So the range is going to determine it. Okay. Once again, we have a quadratic. Once again, we have a quadratic here. Okay. But you see that the domain has been restricted to y x is less than or equal to 2. So if I take and write the domain of the function, it's going to be x is less than or equal to 2. And the range of the function, since it moved down 3, it's going to be y is greater than or equal to -3. Okay? And let's go ahead and find the inverse. Y equals x minus 2 squared minus 3. Switch the x's and y's. Okay, add 3. And take the square root, so you're going to get plus or minus x plus 3 equals y minus 2 plus or minus x plus 3 plus 2 equals y. So we got to choose. Okay, so we have a plus and a minus. We have a plus or a minus. Okay, let's look at the inverse. This implies that the domain of the inverse is going to be the range of the function. So x has to be greater than or equal to -3. And the range of the inverse is going to be the domain. All right. Going to be less than or equal to 2. Okay. We have a plus and a minus. Okay. One of them is going to have a greater than or less than. Well, both of them, if I look at the radicand, it's going to have the domain as x plus 3 has to be greater than or equal to 0. X is greater than or equal to -3. Both of them are going to be that. But let's split them apart. One's going to be plus x plus 3 plus 2. And the other is going to be a minus x plus 3 plus 2. Okay, so we take the radical and we set it greater than or equal to 0 to find the range. Now, all we have to do to make that look like that is we add 2 to both sides. So y is going to be greater than or equal to 2. Is that my range? No, I need one that's less. Well, to make this look like that, we have to multiply it by -1 first. So when I multiply both sides by -1, negative x plus 3, look what it does to the inequality. It flips it. Okay, and then I'm going to add 2 to both sides. My computer's slowing down. Plus 2 to both sides. So it means y is less than or equal to 2. So I need the negative. So f of -1 of x is going to be the negative x plus 3 plus 2. And you can see this is the domain and range, and that is the function that I need in order for it to be the inverse. Okay, so let's do the next one. Y equals 1 minus y, or x, I'm sorry. Switch the x's and y's. We're going to square both sides. So we get x squared equals 1 minus y. And then subtract 1 and divide everything by -1. Negative x squared plus 1 equals y. Now, guys, this is a square root, okay? It's just one part. It's probably going to look like something else, but it's just one part of a parabola. We have to restrict the quadratic's domain. We have to restrict the quadratic's domain, okay? So how are we going to restrict the quadratic's domain is we're going to find the domain of this function. Domain of this function is going to be, let's see, I'm going to take 1 minus x greater than or equal to 0. So negative x greater than or equal to negative 1. And x has to be less than or equal to 1. That's my domain. So x such that x has to be less than or equal to 1. The range of the function is going to be just y is greater than or equal to 0, because you didn't do anything else. Okay, so the domain of this now is going to be, domain of the inverse is going to be x is greater than or equal to 0, and y and the range of the inverse function is going to be x is less than or equal to 1. Right? It's reflected and then less than. Okay, so this is a complete quadratic. For usual quadratics, the domain of all quadratics is all real numbers, but we got this restriction from the inverse. So my inverse function has to include that restriction where the domain has to be greater than or equal to 0. That's my complete answer. If you leave this part off, it's wrong. That must be included in order for you to answer whether or not that these two are inverses. And plus, I put the g on there wrong. Now they're inverses. G of x and the inverse of g of x with the restriction on x included. Okay, next one. Let's go ahead and x plus 2, switch the x's and y's. Okay, divide both sides by negative 1. I'm going to square both sides. When you square a negative x, it just becomes x squared. Okay. And then, let's see, x squared minus 2 equals y. Okay, so once again, in a complete parabola with the domain being all real numbers. But let's take a look at this function here. We have an x plus 2 has to be greater than or equal to 0 for the domain. So the domain of the function is x is greater than or equal to negative 2. Now the range of the function is where it takes square root of x plus 2 greater than or equal to 0, multiply both sides by negative 1. When you do that, it takes the inequality sign and flips it. So you get the range of the function being y is less than or equal to 0. Okay. Now, for this inverse, for the inverse, the domain is going to be switched, and the range is going to look like that. We can't have the domain is not the same as x is less than or equal to 0. So we have to restrict it. F of, this is also g again. So we have g of negative 1, x is the quadratic, but we must limit its domain to x is less than or equal to 0. Okay, good job. Now let's move on to transformations. Okay, we need to find g of x and write the equation for g of x. So the pink is the parent function. The pink one right here is the parent function. Right here and right here. So I can compare the tables. Parent function 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. And then let's go ahead and draw the transform function table. It looks like that's pretty compatible, isn't it? Is it 2? So we still started at 0, 0, and then we went to 2, 1, negative 2, 1. I could just use those points, or I could use 4, 4. If I wanted to. Negative 4, 4. How did all of these points increase? They multiplied by 2, guys. The x multiplied by 2. The x is multiplied by 2. Multiply this by 2, multiplied by 2, multiplied by 2, multiplied by 2, multiplied by 2. Okay, so to create that function, and nothing else happened, I mean, that just pretty much takes care of everything. The x's got multiplied by 2. Okay, so what I'm going to do is, since x is a horizontal, and it got multiplied by 2, that's a horizontal stretch. Okay, so the original function was g of x, or f of x, was f of x equals x squared. Now I have to put that 2 back into multiplying the x. And remember, we have to take a reciprocal when it's inside the function. So it's going to be 1/2 x squared. And it was a horizontal stretch. Okay. Next, let's take a look. The pink is the parent function. So once again, I can just compare. 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. And then let's look at the transform functions. First of all, I know it reflected over the y-axis. Okay, let's go ahead. It's still 0, 0. That looks like a negative 1, negative 2, negative 1, negative 2, and then a 1, negative 2. And I'm just going to use those points. Okay, it looks like, first of all, it looks like the x values got multiplied by, negative 1. Okay, to produce those. And then the y value got multiplied by negative 2. I'm wrong. Okay, so that's not right. The y values just got multiplied by a negative 2. 0, negative 2. I just wrote it wrong. Rewrite this as 1, negative 2, negative 1, and negative 2. And that way, you can see that literally each of the y values just got multiplied by a negative 2. Like that. Okay, so I'm going to take the original function. And when values get multiplied or added, you don't have to take the reciprocal. You can take it as is. Okay, so it's going to be multiplied by a negative 2. So I'm just going to do f of x equals negative 2 outside of the function. And you could write it like this if you want. Okay, you could literally write it like that. And that's it. Oh, by the way, these are g of x. Okay, good job. Let's take a look at the next one. Okay, here is the parent function. Let's go ahead and write the points of the parent function. I have a 0, 0, and a 1, 1, negative 1, 1. I could put a 2, 4 if I want. I could put a negative 2, 4 if I want. And then let's look at the transform functions. First of all, our vertex moved to 3, 2. Okay, 0, 0 to 3, 2. That already gives me a hint. Okay, and then 4, 3. I have a 4, 3, which looks like that's the point that moved. And then this point probably moved here. So I'm going to just match those up. And I have a 2, 3. Okay. Looking by it, nothing got multiplied. I'm just going to take the vertex and I'm just going to add numbers to it. You just add 2 to here and you add 3 to there. And could I do it for this one? Add 2, add 3. Will I get? Yep. And then add 2 and then add 3. That'll be 2, 3. Yep. Exactly, that's all that happened. So I'm going to take f of x equals x squared. And remember, the numbers that you add to 2 or multiply, you don't have to take the reciprocal because you're putting it outside of the function. Or remember the other way, the European way, okay? If I put it on the other side, you have to take the opposite and reciprocal every single time. But so you can write it like this if you wanted to. You don't have to. Yeah. And then x has to go inside. We have to take the opposite. We have to take the reciprocal of both. Or we just say that. Now let's go ahead and change that to g. Okay, this way you take the reciprocal of both. You take the reciprocal of both. You can write it this way. Or the way that you used to, take the opposite when you add or subtract inside the function with the x, and you keep it as is. Doesn't matter. Oh, by the way, the previous problem, and I'm having a hard time. My computer's just wonky. Oh, goodness. This right here was a vertical. It was a vertical stretch. And it's a reflection over the x-axis. And this function, we moved it, well, right, 3, and up 2. Okay. Let's do the next one. So once again, the parent function, 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. Okay, let's see where the vertex moved. The vertex moved, it moved negative 3, negative 5. So that means I got that. Okay, I got that from subtracting 0, minus 3, and then minus 5. Okay. Let's look for a clear point. I don't really see any clear points. I'm going to say that that is a -1. Okay. -1, 1, and a -5, 1. It's kind of unfortunate that I put this graph. This is going to involve a little bit more, but let me go ahead and just try to figure out what g of x was. Okay, so from the things that we already know, I don't know the a value. I know that there's going to be some kind of a value, but I do know that my equation so far is going to be a +3 squared and a -5. Okay, there are several ways to find the a value to see how this stretched vertically. We definitely know that it is going to be, it looks like it's going to be a vertical, looks like it's going to be a vertical stretch. Okay, that it got narrower. Okay, or it could be or horizontal compression. But rather than putting the number, the multiplication number inside the x, inside the function, it's easier to put it outside. Okay. Another way to find the a value, we definitely know it's a vertical stretch. Let's go ahead and write that down. Vertical stretch. And we know that it goes left 3 and down 5. Okay. To find the a value, we could use one of the points. We can use that point. We can use -1, 1 if I wanted to. -1 + 3 squared -5, and that becomes a 6 equals a, and 2 squared, and then that becomes a 4a equals 6, and a equals 3/2. So that gives you the actual the scale factor. Okay, so 3/2. I'm just not. And x + 3 squared -5. That could be your final answer. Another way you can find it, and we haven't gone over this, is that I said the first clear point from the vertex for parabolas and most other functions is let's see, is going to be like kind of like slope. Okay, so if you look with this function, and I don't want to confuse you, but if you go look at this next point, it's right 1 and up 1. And then if you look here, it's right 1 and then it's up about 1.5. And it's not clear, you have to kind of estimate. Up 1.5. Okay, so if it's right 1 and 1.5, 1.5 written is 3/2. Okay, and up 1.1 over 1. So that's actually 3/2. You can do it that way. You can always go right and see how much times you go up, and that's actually going to be the a value on your vertical stretch or compression. Not compression, just the stretch. Okay, so once again, I don't want to confuse you. I found the a value using the things that we already know. And I already know that it was a vertical stretch because just by looking at it, it looks much narrower than the pink graph. Okay, but I'm happy if you could just tell me, like if you went left or down 5, and it gets more complicated when we add a vertical stretch to it because we haven't gone through and actually looked at the table and saw whether or not we multiply the y values by 1.5 and then add 5 or subtract by 5 or the opposite. We haven't done the actual order of operation when it comes to transformations yet. Okay, good job. Okay, now we're